Good afternoon, everyone, and welcome to the Construct Innovate Webinar Series on modern methods of construction. This week, we're going to continue to focus on housing for all delivery, but with a more focus from the designer's point of view. So we'll have the design considerations for modern methods of construction. My name is Jamie Goggins. I'm Director of Construct Innovate, which is Ireland's National Research Centre for Construction Technology and Innovation. I run this webinar series in association with Engineers Ireland West Region. So we're very lucky to have four fantastic speakers this afternoon in there, so which will give us different perspectives from different professionals. So the first speaker is Donal O'Donoghue, who's the director of COADY Architects, and he's going to get the architect's perspective. Then we'll have Eoin Ryan, who's director of Ryan and Associates, and he's a fire engineer, so he's going to give the perspective from the fire engineering side of things. Then we have Declan Wallace, CEO of Evolution Innovation, who provide a lot of support to companies that are trying to get certified for modern methods of construction, and he's going to focus on fire testing, which is an essential step in getting modern methods of construction products to the market. And then we have Dr. Eoin King, who's a principal investigator in Construct Innovate at the University of Galway, and he's going to talk about sound engineering and give some sound guidance for modern methods of construction. So during the webinar, if you want to ask any questions to the presenters, please post those in the Q&A at the bottom of your screen. So you'll see at the bottom of your screen the Q&A button, so post them in there. We'll deal with all the questions at the end after the four presenters have finished in there. The webinar is also recorded and will be available later on the Engineers Ireland channel on YouTube as well. So without further ado, I'm going to hand over to Donal. So Donal is going to give his first presentation. So hand over to you, Donal.
Okay, thank you, Jamie. I'll just share screen now. Okay, go to presenter mode. Okay, so thanks for that, Jamie. I'll keep an eye on time, conscious we have to get through quite a lot. So I suppose Donal O'Donoghue here, Director of COADY Architects. So we've an amount of experience in offsite construction going back, I suppose, the last 20 years of my career, but it's between panelized and volumetric. So this presentation is really focused on housing and the design aspects. And there's a number of images that some may be familiar with, which are using some of the learnings that we have from a recent project with the OPW for Ukraine housing, which was all volumetric focused MMC delivery. So the aspects I just want to touch on is that the main design constraint being the size of the module and how that applies to both single story and two-story. The design, the temporary weathering and the storage was a key consideration for throughout and applies to all offsite construction. Then the connections of the modules on site, both module to module, using the foundations, the services, and then just the point being the front end, the design focus that needs to go in, the coordination that needs to happen prior to commencement on site, and looking at everything from the site works through. So I'll go through this at a little bit of a gallop because there's a number of slides to go through. So the main constraint really is the ability to transport and deliver units, and the OPW went with the approach that it was to be a pre-weathered single story unit. So the size that fits on a flatbed truck, 4 meters by 14 and 14 meters long, really within the constraints of making sure that there was no need for police escort, but it still had the requirements of having to be delivered in non-peak hours. And that obviously puts constraints on the layouts that we could consider. We've applied that as well to a two-story version for the same building program. And we looked at providing a three-bedroom, two-story house. So downstairs toilet, kitchen, living, dining, and upstairs there was 3 bedrooms. And one of the considerations in this instance was not just the maximum width, and the length was actually the maximum height. So 4.2 meters was the maximum height permissible to make sure that we could get beneath bridges and crossovers and motorways. So you've got the key dimensions and the X, Y, and Z axis to consider. Temporary weathering is another consideration, because as quick as modules may be able to be built and units be able to build off-site, the site may not be able to receive them as soon as they are ready. So there is going to be a period for them to be considered to be in temporary storage, but also in transit. And even when they're on site, there's an amount of work that needs to be done on site to complete the external finishes, whether it's from a structural point of view, part E for sound, which we'll hear more of, part B from a fire point of view, thermal point of view, and just simple weathering. So the units have to be able to withstand an amount of exposure to the elements in their temporary state. That also includes the lifting. So you can see in the center image, there's 8 lifting eye units. They were through the top of the parapet. So to get that weather, the temporary weathering in place to allow that lifting happen and allow the on-site completions of the roofing. And the center image as well shows the module being transported in a full polythene wrap to again keep that I suppose protected as it is in transit on the back of the truck. One of the key issues that then has an impact, that temporary weathering, is when we're considering multi-story units or back-to-back units, is the need in plan to have either an acceptance of an open module or the provision of a double wall. So you could see the image on the left-hand side in plan, both of those units, which are placed side by side and completed, they actually had a full wall beside them. So you've got that depth of wall, and as they're actually placed on top of each other in a multi-story function, there is a full double floor and ceiling buildup. So the bottom unit can be left in place for an amount of time before the upper unit is in place, so it isn't an open module. So that provision for the double structure, allowing for the ceiling height that you're designing to allow for, it has a deeper floor overall floor structure, which means the stairwells need to be designed to allow for that greater floor-to-floor height. So in a traditional structure that might be, or traditional on-site, that could be kept a little bit thinner, but for off-site construction and MMC, once you know that, it can be designed for, but it does mean you probably aren't introducing an extra riser into your stairs. Then the connections on site, making sure that the connections between the units in both plan and in section allow for the structural connections, the completions of fireproofing, and there is a complete vapor line, and then thermal insulation on the weather line is able to be completed, and making sure there's clarity about how the off-site construction has been finished in a way that it is robust and can be then have the finishing trades happen on site. And in this instance, it was trying to optimize that balance between off-site and on-site. We did introduce a temporary roofing sheet. This was brought through in kind of considerations with the manufacturers in the off-site state, that while it was in transit, there was deluge of rain might come, and making sure that there was an ability to weather the exposed surface of the lid of the lower unit. So there was actually a temporary roofing sheet put in place that when the unit was in place, it could then be taken away, and because it was obsolete at that point. So it was just, again, that temporary weathering aspect to be considered. Plan junction, same thing. It's how do you get the fire completeness in place. So the back-to-back of those modules, how tight can that realistically be? It's shown there in place that there was a 6 mil gap between the two, which allowed for a 10 mat fire barrier to be put in place. We demonstrated that the ability to get that tolerance off-site with a series of mock-ups. So we built smaller scale versions, or full scale, but small portions of the 4 modules of these units that we put together. So 6 mil being allowed on site. Could that be delivered? And the whole intent was, in this case, was a 6 unit terrace. So there's 6 3-bed houses, which was an approximation then of the 24 modules that would be put beside each other. And the sequence of that was put in place. So module 1 was put in place, module 2 was put in place before module 3, so that, again, there was a working platform to be able to then go in, complete the fireproofing, and the completeness between modules 1 and 3 from a working platform, and so on as you go through. So there was always a working platform to be able to work at, and again, trying to minimize the need for any on-site scaffold. So the off-site sample that was put in place, you could see that's the aggregation of the 4 modules. So there's an example of the vertical joint and the horizontal joint. There was a soldier course introduced at the joint between the ground and the first floor, and the module between the side by side. The majority of the brickwork was completed in the factory, with a series of brick slips then put in place on to allow that completion on site. And again, that continues all the way through the roof. So the majority completed off site, with the last strip for thermal completeness and for fireproofing completed on site. The foundation connection is the next aspect of it. So the foundations are all completed on site, knowing the key dimensions that were being put in place. So those pad footings put in place for each of the hot rolled steel sections as they come down. So you can see each of the units had 8 points for the hot rolled steel to come down. The units side by side share the foundation footing, so the modules will go side by side and share that foundation, so that work was able to be completed. And you'll notice the foundation pads are sitting slightly proud of a slab, and one of the considerations in this case was we wanted to make sure that we dealt with radon and the radon detailing of this in a very, very robust manner. So the detail we put in place, we raised access, or sorry, what's considered to be a raised floor beneath the units, and had a ventilated zone. So there needs to be, for building regulation compliance for Part C, it needs to be 150 mil vented airspace beneath that, and we had a concrete slab that covered that under space, and we had a vent then that came up through the plinth of the unit, and you can just about see that tracing in the dotted line, which ventilated the underside of the modules again to dissipate radon. Again, this is down to not the inability really of being confident about a complete radon membrane where modules have been put together. The basis of compliance with that was considered in a good amount of detail to make sure that the ventilation of that suspended floor had the sufficient wall venting space. So there's 1,500 square meters or square millimeters of free area for every linear meter of the external wall. So we calculated the linear meterage of the external wall and put in a vent that would sufficiently ventilate that space. In the single story units, it was a slightly different approach, where we took vents from that subfloor out to the pathway. The services is the other aspect, and a lot of early coordination into how the services get to the site, whether it's the ESB or the incoming live services, and how they then connect into the modules as they arrive. And the commissioning of those services is a key aspect. So the wiring would happen off-site, but then they would be brought together into junction boxes and then brought into the incoming services, which making sure that the MPRN number was able to keep going all the way through. So significant amount of coordination then in that site stage, making sure that we're able to get the drainage services, Irish Water coming in as well, but then the consideration of the electrical services. You can see on the left we had them docked against the unit, but that necessitated the service wall to be completed after the module arrived on site, and we have looked at actually putting it in a median away from the unit so that they could be completed and give more working space for the modules to be delivered and completed on site. And then there's just some images of those as they come through. But you can get a sense that there really is the need for that very early design consideration of the routing of services in the modules, how they connect together, making sure that there is enough access points for them to be connected, and then how they connect to the site services and the sequencing of the site versus the delivery of the modules. So that is very, very quick gallop through. And Jamie, hopefully it wasn't too quick.
Brilliant, that's fantastic. I'm sure there's going to be lots of questions for that as well. So I see them coming in already. So if you have questions, please post them in the Q&A, and we'll come to those at the very end. So without further ado, I'm going to hand over to Eoin Ryan. So Eoin is Director of Ryan and Associates, and he's going to give us from the perspective of the fire engineer. Thanks, Eoin.
Hi, can you see that there? Yeah.
Yep, perfect.
Hi, Hi, I'm Eoin Ryan. I'm a director of Ryan Associates. I'm a former assistant chief fire officer and in self practice for nearly 18 years. So we've dealt firsthand with a lot of issues with regards to MMC and other types of applications, and what I'm looking at as key considerations from a design point of view and practicalities on site. I'm just going to run through some of the issues that we've seen on site and some of the issues that will need to be taken into design for future consideration. So we're here looking at today, we're looking at MMC and their compliance with Part B of the building regulations. So obviously the benefits of MMC is the time efficiencies, cost effectiveness and sustainability, but with all of that, there is a lot of issues with regards to, or potential issues with regards to fire safety and compliance with Part B. Like, these are the types of construction that we have worked with: ICF, CLT, which is cross-laminated timber, structural framing, as in light gauge steel, timber frame housing, modular pods. All non-standard construction methods should have an agreement cert, an NSAI cert, and all buildings must comply with parts A to M of the building regulations. Just to go back on this, where a lot of onus comes on this when it's has to go through a third party, and there's requirements for either building control or for fire departments to assess the methods of construction. Dwelling houses do not need a fire safety certificate, so if you're submitting a compliance report, it'll be assessed by your architect, your engineer, and then also by the building control authority. And depending on the building control officer, they may request further information on the construction methods being used, and particularly on different junctures of the building, how you're addressing whether it's compliance with Part A, Part B, Part F. So, and that could, generally for houses, it could be the building control officer coming back looking for additional information on that. For commercial buildings and most MMC buildings that are constructed are new buildings, so it's they would need a fire cert where there are multiple units, as in stacked on top of each other, not terraced. So works in connection with design and construction of a new building requires a fire safety certificate, and then this falls in under the scrutiny of the fire department, who look at all the methods of construction, the floor build-ups, external wall build-ups, and the junctions where there's cavities or where there may not be cavities. And this throws greater light on what's required, and depending on the local authority, they may sometimes cause a roadblock to a method of construction being used. And we've also seen where, in some instances, where insurance companies aren't fully comfortable with new methods of construction, so they can also look to not allow a certain type of build to happen. They're getting more comfortable with it, but it has happened on a number of sites over the last 2-3 years. So just going to run through the fire safety regulations. With regards to this, you have to comply with Part B of the building regulations. Non-standard methods of construction are proposed. If they are proposed, the fire department at any stage may request additional information, seeking testing information, clarification on connections, elements of structure, and they want to demonstrate a demonstration of compliance, how surfaces penetrating fire barriers are to be treated. If you aren't able to provide this, it may not be possible to get a fire safety certificate. And a lot of products aren't certified for certain types of construction, and some are for others. And it's becoming more and more prevalent on site that products, when you drill down into the certification and the testing methods of these, they're not fit for purpose. So, and this opens up a lot of questions with regards to different types of construction and products being used in these. So Part B of the building regulations. Part B of the building regulations is broken into 5 sections: B1, means of escape; B2, internal fire spread; B3, internal fire spread structure; B4, external fire spread; and B5, firefighting facilities. With regards to MMC, B1 and B5 wouldn't really be applicable. It's sections B2 to B4 are the relevant sections of Part B, which are relevant to MMC construction, and particularly where you have multiple unit developments. I'm going to run through each one of these sections just briefly, just kind of give an outline on what's required. B2, internal fire linings. So section B2 looks at internal linings and how these can help fire grow and spread within a room or compartment. It provides restrictions on walls and ceilings in circulation spaces and large rooms to comply with certain designations. Class 0 or Class B is generally the requirement for circulation spaces in multiple unit developments and also in large rooms. So what it's trying to do is limit fire spreading up along a wall or ceiling and spread throughout a compartment that affects the means of escape and life safety. It also looks at thermoplastic roof lights and fire-resistant ceilings. B3 is internal fire spread structure. And just the regulations state B3, a building shall be so designed, constructed, and event of fire, its stability should be maintained for a reasonable period. This is also for life safety and for the safety of firefighters who have to go into a building. A wall common to 2 or more buildings should be designed and constructed that offers adequate fire resistance. And a building then throughout should be subdivided so as it restricts fire spread. And again, where you have concealed spaces, there should be provided with adequate cavity barriers are constructed in such a way that fire doesn't spread in concealed spaces. So section B3 generally looks at restricting a fire from growing and spreading from within a room or compartment and restricting fire spread from one compartment to another. Walls and floors have to have a particular fire rating in terms of REI, which is low bearing insulation and integrity, and this must be maintained for each type of building. So the remit of B3 is to maintain a fire within a compartment and not let it spread further or into the external wall or out from that compartment until the fire department come and firefight and extinguish the fire. B4 is with respect to external fire spread, and the external walls and roof of buildings shall be so designed and constructed that they can afford adequate resistance to the spread of fire to and from neighbouring buildings. So section B4 looks at how fire can spread once it leaves a compartment externally, either into the external cavity, up the external wall, or across an external roof and across a boundary or compartment. New requirements were introduced that require non-combustible insulation above 18 meters and cavity barriers depending on the method of construction. For standard construction where you have an inner and outer leaf of block and brick or block and block, you only seal around with cavity closers on windows. But where you have non-standard methods of construction, you have to provide cavity barriers or fire resistance internally at the junctions of fire lines and external wall. That includes walls and floors. So you have to provide a cavity barrier there. So if a fire breaks into the cavity, it doesn't spread up along it. And also the external surface of a wall has to have sufficient fire resistance that it doesn't spread rapidly up along it and goes from compartment to compartment. We've all seen what happened in Grenfell, which was a combination of both. Those cavity barriers were not existent, and the material within the cavity and along the external surface wasn't fit for purpose. It wasn't designed for a building of that height, but however was used. There is some challenges with MMC because you're introducing compartment floors and walls. This from a fire officer's point of view provides queries in regards to the certification of key junctures, because lots of MMC and most fire testing is just done on the floor and ceiling and from each side of a wall. So in terms of fire resistance, walls are always from each side and floors or ceilings are from the underside. There's other junctures and junctions within a building that haven't been tested, and that's fine for an NSAI cert, but it throws up some questions from fire departments with regards to the overall fire resistance of these elements and of the elements of structure. There are also height restrictions on this, and this can affect the rollout of large scale MMC developments, as Part B doesn't allow for this without fully tested details in all of these junctures or junctions. Table A1 here is just an extract from Part B of the building regulations. This is where the required fire resistance for each element of structure, and you need to achieve this based on the purpose group from which the building has been built for. So you have to have sufficient load bearing capacity, integrity, and insulation. For floors, and the table on the far right hand side tells you which the exposed face of where you need to protect in terms of fire. So generally from walls, it's each side separately. From floors, it's from the underside. For a structural frame, it's the exposed faces. And exposed is generally exposed to anything that is combustible. We're working recently on CLT, cross-laminated timber, and there's a number of bodies trying to introduce this into Ireland. We're helping advise them on it. It's a product that comprises timber glued together to form a wall or floor. Whilst the calculation can be undertaken on the char rate of timber to demonstrate its fire resistance, the fire department, during the course of a fire safety certificate, or the building control officer may ask to demonstrate that the glue does not impact the fire resistance, or indeed any pressure impregnation of the timber does not affect the fire resistance. CLT has been used throughout Europe, and calculations need to be taken to account for national requirements. So the guidance, we'd have to look at testing this product under structural Euro codes, and currently there's no real provision under Part B to allow CLT unless you demonstrate this with the local authority or the local fire department. With regards to compartmentation, there is other restrictions which can affect MMC and need to be taken into account at design. Compartment walls above 10 meters need to be constructed of materials of limited combustibility, and that provides a limit on the use of timber frame construction above 10 meters. Compartment floors above 10 meters need to be constructed from non-combustible materials. This also limits the use of timber construction. A non-combustible is generally masonry construction or mass concrete. The new draft Part B of the building regulations has restricted the heights on materials of limited combustibility, which is materials used in ICF and LGS above 15 meters. So that means that you're limited to maybe 4 stories in height. Also separating walls of construction from non-combustible construction and running a continuous vertical plane, with the exception of 3-story houses constructed from timber frame construction compliant with IS 440. This again may limit the use of light gauge steel. So unless there is a conjoined thinking with the department on and fully tested methods on these types of construction, it can limit the use of these above certain heights, and fire departments and local authorities may not allow them to be used without proper testing. The certification at the moment requires compliance with ISEN 13283, and also it has to be representative of their end use and their application to which the test meets. It's important to recognise this fact, since as a consequence, the construction product may have several different European reaction to fire classes depending on its end use application. So each test to national tests can vary massively. And an awful lot of construction products that we have noticed on site may be tested for one scenario, but may not be tested for another. Fire stopping and services, just giving a few examples. Fire collars and wraps need to be tested to their specific installation. If they're not tested as per the tested data, they cannot be stood over. And we've seen a lot on sites that people are providing, even though there's guidance from the department for intermediate floors, and the use thereof, and protecting protecting for services that penetrate through and fire stopping. There's only one colour we're aware of at the moment that is tested for colours on flexible floors. That's on timber floors. Then where you have a posi joist or an open web joist, there's greater criteria in how you fire stop these. And while the open web joist and engineered joists allow greater scope and design, they also introduce greater requirements with regards to fire stopping and fire safety, particularly coming in around protected entrance halls, protected stairs, and the products used that penetrate through these floors and these wall build-ups. And also with regards, particularly for MMC, when you're looking at the external fire spread, when you're constructing these, your distance from the boundary has to be taken into account. And if you have multiple units, your compartment floors and your compartment walls. But when designing these, and we've been asked to look at them, a lot of them aren't designed specifically at meeting the requirements for external wall build-ups in a boundary condition, because they're created on a factory and then they're built for kind of a standard. But if they're close to a boundary, you may need to provide 1 hour fire resistance and 60 minutes fire resistance from the inside and 15 minutes insulation. Also, if the combustible material on the external wall is greater than 1 mil in thickness, this can be considered to be having a certain requirements with regards to fire resistance. You have to take the enclosed rectangle that it's considered to be an unprotected opening above a certain size, and 50% of that elevation may need to be calculated in your distance to the boundary. So all these small things need to be taken into account, and it can affect the use of like these great systems in the rollout of developments. Then with regards to where the system has an NCI argument cert, it is deemed to be compliant. However, B4 still needs to be considered. No deviation from the agreement cert is possible, as consultants cannot stand over it. We have looked at numerous agreement certs from different product manufacturers, and the way a lot of the NSCI certs have been worded, it leaves room for scrutiny, and this leads to fire departments and building control departments come back looking for further information. And if you do not strictly meet the requirements or what is stated in your argument cert, the fire departments generally won't give you a fire cert, and it can delay like the finishing of a building, or you have to try and justify it. And we've seen on a few projects where a client may have had to go and get a juncture or a junction tested just to meet the requirements of the local authority. So the NACI certs, while they're great and they detail a lot of the requirements of the system, it does leave some gaps, and we are looking alongside Construct Innovate of ways to actually ensure that all of these junctions are tested, and it removes all ambiguity for people to make in the decision process, and so allows MMC to be rolled out on a bigger and larger scale. So that's it, and thank you for listening, and I'll answer questions at the end.
Brilliant, thanks, Eoin. Good detail there on the requirements in terms of the fire engineering to meet the building regulations. So just conscious of time, so we'll move on to our third speaker. So our third speaker is Declan Wallace from Evolution Innovation, and he's going to go into more detail on fire testing, which is obviously an essential part of getting your agreement cert to be able to get your product to market. So over to you, Declan.
Let's go. So, okay, so very quickly, following on from Eogain's presentation, I'm going to follow on nicely and delve into fire certs for MMC buildings. So very quickly, who we are, Evolution, we're kind of world experts in modular and panelized. We've been working this game for a long time. We specialize in 4 areas where we're energy consultants, but we're also structural engineers. And we also do a lot of R&D, and on the R&D side, we do about 50 structural fire tests a year in MMC, and we would have done to date about 400 plus structural fire tests, everything from walls, panels, floors to full-scale testing. And then also in that, we more recently in the UK on the more complex buildings, that be buildings over 18 meters in height, we would do thermomechanical modeling, which is structural fire engineering for buildings. Okay, so that's just kind of background on the kind of wide breadth of services that we offer within Evolution. So just a quick track record of what we've done. So we've done education, we've done healthcare, we've done hotel beds. Now all of these are done with MMC products. Okay, all sorts of systems. We've done over 8,000 student hotel beds, 10,000 residential units, and we've done over 12,000 student beds. Now, predominantly in the UK and in Ireland, but the majority will be in the UK. And following on is what we've also developed over 20 and certified over 20 building systems from panels to modular systems across the UK and Ireland. Okay, so that kind of gives us that kind of highlights that we know we're kind of talking about. So we're just going to talk about category 1 and category 2 systems predominantly. Category 1 is volumetric and category 2 is panelized, predominantly LBS. So just following on, what's very important is we have the hacker report came out following the Grenfell report, and what that highlighted was the importance of offsite systems and the importance of system-specific testing. And key thing is, has the offsite system got the system-specific test? Okay, so in addition to that, and following on from that, so an organization called CROSS. So CROSS are the Collaborative Reporting for Safer Structures in the UK. They're an independent organization in the UK, and in 2022 they published a report on concern about internal load-bearing walls being exposed on 2 sides. So an internal wall could be could be exposed from both sides simultaneously and should therefore provide required load-bearing fire resistance for such structure. So this was a query that came up in June 2022. And the idea here was that if this situation happened, it could lead to premature failure. And I think what's more important here is okay, in this situation, the cross-report asked the question of the LGS industry to answer this question. But I think what's very, very important is this issue has been directed at steel frame, but it applies to all construction because you get the same scenario in any construction. And the key thing here is walls nuts. The key thing. So this was very important, right? So the implications report suggested an issue with structural failure of an internal load-bearing wall. The implications across were very serious. Fire authorities in Ireland began to refuse to issue fire certificates for buildings until this question could be answered. This led to developers, contractors, and building professionals excluding LGS as a solution for mid-rise buildings, because LGS is currently used in mid-rise buildings. If not resolved, the effect in the LGS industry would be disastrous. So it was imperative the solution was found quickly. So that's what we were approached as independents to look at the situation. So we're asked to prove wall stability with fire from both sides. However, no standard, it's very important, there's no standard of wall for fire testing or wall from both sides existed. So obviously demonstrating compliance with exposing the fire from both sides simultaneously is much more onerous than when exposing a fire from one side. So you can see here on the right hand side, this is a situation we put a wall in. So think outside the box, Evolution above and beyond, design a unique test method to cater for this unprecedented challenge, right? And how we did that was basically we identified a floor test rig, and we were able to test the wall from both sides. So this was only the start. We did it to work with the fire authorities, work with bodies, and other circles to convince them. So the execution. So our product development and structural engineering teams analyze the problem from first principles. Because of the unique nature of the test, no test rigs existed for this type of test. So we worked with the test lab in Belfast to design a wall panel that could be built within an existing floor test rig without affecting the fire curve. And this was a worldwide first. So you can see here we used a floor rig, and this is the picture how to sit inside the rig with the wall being exposed basically on all two sides, but in some cases 4 sides, all 3 sides. Okay, so what was key about this test? The test was that we managed to follow the ISO curve perfectly, and that's key to the test. So we're trying to design a test that follow the curve. The standard single-sided detail incorporates 2. So in a normal elemental test, 2 12.5 mil boards would have as Eoin would have limited across from one side only, but this requirement was to test it from both sides simultaneously. So by enhancing the walls, 2 15 mil boards, we're able to keep the steel within the maximum temperature range for more than 60 minutes. So we're able to, by enhancing it from 2 12.5 to 15s, we're able to deal with this 2-side exposure scenario, which is very important. So the problem is solved. So this demonstrated we had a simple, low-cost solution to address the concerns raised in the cross report. It's very important, though, the cross report is not a legal requirement in Ireland and is not part of the building regulations in Ireland or the guidance documents. However, the question was asked, so we felt we had to answer this question, and obviously the fire authorities wanted this question dealt with. So moving on then with the fire safety cert, and mainly dealing with B3 internal fire spread structure. So we then worked with Dublin and Cork fire brigades to discuss how we deal with this. So what was key to this at the beginning was there could be no change to fire strategy. So no matter what the building was, there'd be no change to fire strategy. So internal load-bearing walls, and there's 2 tiers, contain the fire. So internal load-bearing walls exposed to fire from each side separately. So this was a scenario we did not have a 2-sided exposure on a structural wall. So examples of this would be very common would be in co-living hotels and student accommodation, which I'll explain shortly. And then the other scenario was where it was exposed both sides. So again, no change to the fire start. Internal walls could be exposed to a fire exposed on both sides. And examples could be apartments and other building types. Okay. So just showing you here on the contained fire strategy, this would be hotel or student accommodation. And what's very important here is we worked with the fire brigade to agree this. So a compartment wall, see here, the blue wall here would be compartment wall. These yellow walls would be structural walls, but it was agreed there would be fire doors here, starting with fire doors. So fire would start here. So it was agreed in this strategy that in this situation, the yellow wall here, for example, would not be exposed on both sides because it had to go around the wall, 2 compartments. In logical sense as a managed building. So that was the agreement for contained fire. Now, in the apartment scenario, which is a much more challenging scenario, we could have a door and a low-bearing wall within the apartment structure. Now, even if there was fire doors within the apartment, this is not a managed building, and some of the doors are open. So on that basis, it was agreed that in this scenario, we would protect the wall from both sides, and that is the scenario. So it was not feasible. So part is so that's how we did that one. Okay. So what was key then was, at the moment, when we look at how a fire site is developed, we recognize that there needs to be a fundamental change. So what you're seeing here is a traditional process for achieving a fire safety certificate on a building. So we have the architect's drawings, we have the fire consultant's fire safety fire strategy, and then ultimately the building is going to go to whatever technology, and then the structural engineer engineers the building, and then the fire consultant is left out of the loop. So fire consultants are not provided with structural drawings, and the structure is not provided with minimum periods of fire resistance for elements of structure. So that was a bit of a flaw. So we've now developed a new process with the fire safety officers to go over this process. So now we identify, we get the architectural plans. The method of construction is let known to the fire safety consultant, and the fire safety consultant does these fire safety stuff based on the structural design of the MMC technology. In this situation, we'll take it's like HD, it could be modular, and as you see, you're identifying all these load-bearing walls, which are load-bearing, which may not be the case in another form of construction. Then the fire consultant issues the fire safety strategy drawings, following what Eoin said, in much more detail, identifying all the minimum periods of fire resistance fully laid out. And then, so in this case, the fire consultants are provided with structural drawings, and structural engineers are provided with minimum periods of fire resistance for elements of structure. And therefore, on that basis, then we have structural engineered fire resistance verification on this thing, and more importantly, the structural engineer does the fire limit state calculation. So in the fire safety certificate, we are under B3, internal fire spread structure. The structural engineer, there's a methodology where the structural engineer confirms the fire limit state. The building has been designed for the fire limit state and the loads the building is taking. Okay, so what you're seeing here briefly on screen is you're seeing a typical fire safety certificate that would come for a normal traditional building. As you can see, you just have your basic compartment walls, and what you're seeing now is you're seeing an updated one where we're identifying all the load-bearing walls, the different periods of fire resistance. For example, the green wall would be an external wall, and that would have an out and out-in fire requirement, and therefore the manufacturer of the product would provide an out and out-in fire test for that wall. What you're seeing here then is you're seeing a compartment wall, which again will be exposed from one side separately, and then you have the orange walls, which in this case would typically be 1 hour walls exposed on outside. But in a scenario, you could have a wall that's exposed on 2 sides, and that wall then would be flagged to be not in this area, but you might have a 2. So in that case, if there was a 2-hour wall exposed both sides, then you would identify that wall and you would provide a test for that wall on both sides. Okay, so that's briefly summary up. So in conclusion, there needs to be a better understanding of how structures behave in fire and how to treat them in all structural forms. Fire design needs to involve more than one kind of specialist. That's very, very important. You need structural engineers, you need the fire consultants, all working together. The fire brigade should know what MMC they are facing before they enter the building. I suppose at a higher level, industry full-scale training should be carried out, but due to expense, it should be carried out by support by government. You will need you will see a greater move to interactive and system fire testing, but there are no harmonized standards for this. So again, this is a very quick presentation that you today, and I've seen the other presenters, they can spend a lot more time going into a lot more detail on all of this. And it's quite a complicated field, but as you can see, so thermomechanical modeling and calibrated heat transfer modeling will be critical for future structural fire design. So as we get into more complicated buildings, bigger loads, we'll do thermomechanical modeling. On-site QC for fire stopping needs to be in line with the quality in the factory, and that's very, very important. And again, in the UK, you're seeing the building safety bill coming in the UK, and there's some very good policies coming in there, which hopefully will be adopted in Ireland in the coming years. There still needs to be a place for desktop assessments once they're taken, but we require skill and knowledge. And there's too much leniency now to test everything now. when some very basic assessments can do. And not every assessment is simple, but I think there's too much. We've gone too far at the moment where assessments are very limited now as for the extended field and application, and I think this is a challenge because we're doing lots of kind of over the top testing, in my opinion, which is very, very expensive, and obviously it's tying up the test labs. And most importantly, meet with your local fire officer and building control at design stage to answer any questions they may have following on. And very important, avoid 7-day notice applications when using MMC. You should not do a 7-day notice when doing an MMC application. Jamie, I kept that very quick because I'm conscious of your time, and that's it.
Brilliant. Thanks, Declan. That's fantastic overview as well. Just to remind people to put your questions in the Q&A, and we'll deal with all the questions, or as many as we can anyway, afterwards. So just without further ado, I'm just conscious of time again. So we've got our last speaker, last but no means least, is Dr. Eoin King, who's the Principal Investigator in the University of Galway within Construct Innovate, and he's going to talk us through the sound engineering. So give us some sound guidance for MMC. Over to you, Eoin.
Very much on the purpose. Residential will have different needs to commercial properties. Commercial properties will have different needs to educational. Educational will be different to theatres and so on. So let's skip through those anyway. But in essence, this is all informed by Part E. It was mentioned earlier on of the building regulations, which for the first time introduced real standards for sound in buildings. They focus on two main things: stopping sound transmission, which is the reasonable resistance to sound, and reverberation time. And again, it depends very much on the application of the building as to how those two issues are dealt with. In terms of our traditional approaches, yes, they're fed by the building regulations. They often lead to some kind of typical errors, which would be a lack of proper sound insulation. Inadequate planning, oftentimes we don't include the zone approach to acoustic design, which is essentially kind of common sense. Don't put a bedroom beside a machine room, or don't have a bedroom overlooking a motorway, things like that. In the past, noise control measures were often thought of an afterthought. It wasn't included in an early stages of the design. Acoustics was often seen as kind of the second or the last thing to consider. That's changing, which is good, because acoustics should be an integral part of the design from the outset. It's been recognized as an issue of concern. It's included in building regulations, but even more advanced certification like the LEED Green Building Certification and WELL Building Standard, they include sound as a concept that needs to be addressed in order to have appropriate buildings designed for occupants. There are some opportunities for modern methods of construction. Here we have our standard mass law, if we like, the effective transmission loss. The higher the transmission loss, the better against frequency. It's generally controlled in this region here, the mass law region, where it's a 6 dB per doubling of mass, which means that the heavier walls give a better sound transmission. What we can do is we can alter this slightly by using sandwich walls. So this can be changed using sandwich walls. Here's an example here. And what's quite exciting at the moment is the use of acoustic metamaterials. So acoustic metamaterials are using materials slightly outside the range what they were intended for to improve their overall performance. So we've got some ongoing research in that area. The idea of prefabs and modular constructions allow for a lot more flexibility in design and precision in design, which can lend itself towards acoustic improvements. And proactive planning. By integrating acoustics into the early stage of planning, we can take advantage of a number of advances in computational methods. So we can use computational methods to optimize our design, but also we can actually use methods now to listen to actually hear what a new room will sound like before the room is built. So we can make adjustments to that. We can listen to it and determine, which is a very useful or a very cool trick to show clients and things like that. But opportunities come with risks. The idea you know, we're moving towards more lightweight material. That's going to have an impact on sound. So less mass in our materials may mean less mass to stop the sound transmission. So how do we address that? I think acoustic metamaterials are the answer there. Sorry. We've got potential difficulties in controlling vibrations and resonance, particularly in prefab units. And maintaining consistent acoustic performance across MMC projects can be challenging due to variations in manufacturing processes, different materials and so on. So quality control measures must be implemented. They should be inspected during construction, and all tests should be performed by a competent tester. And in Ireland, we have the Sound Installation Testing Register, CITRI, which lists those people who are designated as competent testers. But the basic principles of good sound design remain the same. In general, we always want to avoid air gaps, holes, leaks. Oftentimes these could be around electrical outlets. But here's an example of the effect of the area of a hole. So a 0.01% hole. If your area is 0.01% of a gap, your 60 dB, just on the top right-hand corner of this, the 60 dB rated sound transmission wall will be reduced to 40 dB from that small of a gap. So the effect of a gap is very, very significant. Another thing we can do is ensure tight seals and connections to prevent sound leaks in modular construction. What I've included here is the idea of a door drop down. So when that door is closed, it presses a button that drops a seal underneath the door, which stops a lot of sound transmission. Simple things like that can be very, very effective. Avoid direct transmission paths. So here's an old example, but a good one. It's the difference between a standard wood studded wall with gypsum wallboard compared to a double wall. And the key difference between the top figure on the right hand side and the bottom on the right hand side is there's an air gap between the studs and there's an air gap between the fiberglass, and that changes the acoustic impedance. So when we're talking about sound transmission, we want to change an acoustic impedance is good. So a simple air gap can oftentimes be your friend. And it's important to note that sometimes silence is not the aim. Sometimes a little bit of noise is good, and that's often referred to as acoustic perfume, which particularly in offices, it adds to speech privacy and things like that. But ultimately, the main lesson to learn, and if I know I'm flying through the slides here, but if there's one take-home message that you should take from sound guidance or sound design, it's to include acoustics and include the idea of acoustics and sound transmission and reverberation time from the early stages of your project. Because as I tell my students, it's easier to knock down a wall on paper than it is to knock it down when it's built. So acoustics should form a kind of an integral part of your design. I'll skip off these slides really briefly. I was going to talk about some current research we're doing here in Construct Innovate. We've assessed classrooms in Ireland to see how effective they are, and about 66% of classrooms don't meet current standard guidance. We're working on indoor soundscapes using machine learning techniques, and we've just started a project with Construct Innovate on using innovative acoustic metamaterial solutions for sound transmission. All of this information is on our website, the Galway Sound Lab. And just finally, Construct Innovate, we have a good degree of acoustic test equipment now, where we can perform sound insulation tests, sound transmission tests, absorption tests, a wide variety of room acoustic testing software. So I'm sorry for skipping through that, and sorry for the sound issues earlier on in the talk, but I hope it made sense. Back to you, Jamie.
Brilliant. Thanks, Eoin. Thanks for catching up on time as well. It's much appreciated. Brilliant.